Hello everyone. Today we're going to look at the first chapter on trigonometry. It's really important because the second half of the chapter on complex numbers requires this knowledge, and quite an amount on differential calculus and integral calculus requires it. These functions turn up in a lot of different places, so we'll go through it relatively slowly, and hopefully what we'll get is a number of different ways of looking at something that you would already have gone through in school by now. The idea isn't to put across the school's solution method. It's hopefully to complement it by different ways of looking at things. Now, first off, we owe much of the early work on calculus, on trigonometry, we owe it to the Indians. The Greeks didn't figure this out. The Arabs, through trade with India, managed to transport this across into the Muslim world. They did a lot of work on it. And then around the time of the Renaissance and subsequent to it, Europeans really started to work on it. Okay, what did the Greeks know? One of the things that they found out, which was kind of an oddity, and by the way it is in the start of this chapter, they found that no matter how big or small or indifferent a circle was, that if you found its circumference, the length all the way around it, and you divided it by a diameter, that you got a constant. An intriguing sort of a thing. Now, it was very much to their displeasure that that constant wasn't either a whole number, which would have been perfect in their mind, or even what we call a rational number, something that can be expressed in fraction form of a whole number divided by a whole number. So they had to give it a name. And basically we'll write out what we're talking about here. Circumference divided by diameter equal to a constant. And the name they gave to that was pi. So that's where it came from. Now the interesting thing is, once we actually find a relationship like this, it's very often used in a slightly changed form to be able to find out one of the other variables. It's easy, obviously, to work out the diameter of a circle. It's a lot harder to measure out the circumference. So generally, where you've seen it since at least second year, is that the circumference is equal to pi times the diameter. And we know that the diameter is 2 radii, so it's equal to pi by 2r. Now then, what do we know here? We can draw a drawing. It's always a good idea. One of my perfect circles. And we're now going to ask just this angle here, this amount of rotation, a full circle of rotation. What is it? What can we call this stuff, or how can we measure it? What units do we come up with for this? If we stay with the Greeks for the moment, what I would say to you is, it's easier actually to start with radians than with degrees on this. What they actually found, and it isn't surprising because it actually comes straight from this equation here, is that the whole circumference of this is equal to 2 pi by the radius. Now, what we've actually gone and done, believe it or not, is figured this out. That if I let the radius rotate so that this is also r, so in other words, it starts down here and it's let rotate off up to here, so that it has actually tracked out a length that is exactly the length of the radius, we have got 1 radian. Okay? The rotation is 1 radian. Now that's pretty obvious, because if we go and track out the entire circle, if we rotate that whole amount, what we have actually just said is that it's 2 pi r in length, and if you track it out in this fashion, we find out that you get 2 pi radians. It's just straight from this equation. Now the interesting thing about that is, what we're basically saying then is the circumference is equal to the angle by the radius. So for a full circle, we have the full angle of 2 pi by r. If we're looking at an arc length now, where we're saying for theta degrees, and this is obviously a bit of a circle, okay, and there's a radius length r, we can actually work out the arc length, because this is just a scale down problem from the full circle problem, and it basically is saying that the arc length must be equal to the angle by the radius, and in this case theta by r. Okay? So even when we talk in terms of radians, all we're really doing is we're coming back to what the Greeks found, which is that there's a constant if you divide the circumference by the diameter, and it's named pi because it is one of those nasty irrational things that that continues on and on without repeating, goes forever. So both the circumference equation and the length of an arc equation come straight from that. The Greeks again found that for the area of a circle, that it was equal to pi r squared. Now that's interesting, because look at the angle here. It's actually only half the total angle if you rotate around in the circle. So we could expect then that for just a part of the circle, we look at the area of this, we'd expect area to be equal to half the angle by r squared. All pretty straightforward stuff, okay? Now then, technically we're saying that radians is simply another way of talking about the fact that there is this number pi, which you divide the circumference by the diameter and you get pi, which is the same as saying there's 2 pi by the radius of them equal to the circumference, okay? It gives us a measure, it gives us a step. It's like having a meter to measure length. We now can measure rotation in terms of 1 radian, etc. Convention has it that we don't put a symbol after it. Like for a degree, we'll go with a little circle. We can say 36 degrees with a little circle. For radians, you just declare it as it is. If it's pi, you just leave it as pi. If we're looking at 1.5 radians, you just say 1.5. Now, clearly, conversions of these things from degrees to radians is an easy matter. We know that a full rotation is 360 degrees, which is 2 pi, and that tells us that pi then is 180 degrees. Now, if we have something in degrees, let's say we say 37 degrees, and you wanted to find out how many radians it was, well, you always find out what's the price of one of the things you have. So we'll say, in that case, you say 1 degree then is pi over 180, and 37 of them will be 37 times this. If instead we were told that we had 1.7 radians, we would say, okay, having started off with pi equal to 180 degrees, we'll say then 1 radian is equal to 180 over pi, and whatever number you have then we'll multiply into this. Very straightforward stuff, okay? So if we have 2.7 radians, you can say 2.7 radians will be 2.7 multiplied by 180 divided by pi. There's a few things you need to recall from junior cert, because they're definitely going to come in the kind of problems that you get in this chapter. One of them was something you had to prove in your geometry of the circle. If we have 2 radii, and if we go to the tip of each of them and draw a line to another point on the surface of the circle, it's supposed to join at the surface of the circle. What we do know is, if that's an angle A, that one is 2A. Okay? What else do we know, and that you need to know? Well, every time you draw a radius to a circle, the radius is always perpendicular to the tangent at that same point. Okay, why is that useful? There are problems which look like this. Where you'll get 3 circles or 3 spheres, or whatever they may refer to them as, and they may, and in some of the problems they do give you a situation where they'll say, oh, the diameter, or sorry, the radius of this is, we'll say, 3 centimeters. So, and they're supposedly all the same in size, not that they look like it here, but technically they're all the same in size. What do we know? Now, how can we help solve our problems? What we can say is, if I draw my radius from here to this point, it's clearly perpendicular to the tangent of that point. And it also means the same is true for this one. And so if that's 3 and that's 3, this forms a straight line running all the way down along here, and the same will apply running across here and here. We can say in each case the radius is perpendicular to the tangent. So we can use the full radius lengths in each of these. That little piece of information is generally what makes it easy for us to solve problems that do look a lot more complicated than they actually are. Now then, we can solve some really curious problems. For example, like, what's that area in here? Can be solved by this. We can work out, and quite readily we can work out that angle, and that angle. We can work out the area of the triangle, the blue triangle. We can also work out the area of the 3 little pieces of the pie, such as this guy here. And when we take those 3 pieces, that guy, and that guy, away from the area of the triangle, we now have the area of this curvedy bit in the middle. All that's basically done by knowing this over here, that once you have a radius to a point on this circle, the tangent is perpendicular to it. Lots of useful stuff, all from a very simple idea. Now, we know that once we have a right angle triangle, you should always keep in mind our Pythagoras, because that's how you solve so many of the different problems. Okay, but to begin with, let us look at the rotation that's here, which is this angle A, and we will say to ourselves, well, actually, just to keep my convention the same as how it's going to turn out later on, we'll call this one B. Why? Because I've put it across from the B line here. So we're saying, how can I define things? Sine. You will know from junior cert, the sine is the opposite one divided by the hypotenuse. Okay? Cos it's the one that's adjacent to this guy down here divided by the hypotenuse, and tan, which is equal to the slope of the hypotenuse okay, i.e. Okay, in the diagram, that line is the one that's inclined at that angle, B. The tan is the slope of it. So if I actually used geometry of the line, and I came up with this equation, and we'll say it finished up y equal to mx plus c, that m, okay, is tan B. An easy thing to remember. So tan of B is going to be the B over the A, which is the same as sine B over cos B. They're the basics, okay? Now, there are obviously lots of little examples provided in the book to help you in relation to getting familiar with these different things. We have a number of important little relationships that we just have to build now. Yeah. The first is we'll still call this B, and we'll call this angle A. We're still using side C, A, B. Look back to sine of B. What you will notice down here is it's B over C. Now, isn't that B adjacent to A? So what we can say now is sine B is equal to the cos of the A, and also cos B is sine of A. For example, cos B was its adjacent one divided by the hypotenuse. Now that adjacent one is the one that's across from A, so it must be the sine of A we're talking about here. So the sine of A is going to be A over C. Okay, now fundamentally all that's telling us is in a right angle triangle, the cos of one of the other angles is equal to the sine of the third angle, and the sine of the second angle is equal to the cos of the third angle. Because we know all the angles in a triangle add up to 280 degrees, and we have a right angle in there, it means a plus b, okay, are equal to 90. So if I know what cos of 30 is, I immediately know what sine of 60 is. If I know the sine of 45, I know it must be exactly the same as cos of 45, because 45 and 45 are 90. Having really revised what is covered for Junior Cert, what we need to do now is start to look at the defined functions, which are trigonometric functions. And the key to all trigonometry is the unit circle. Any logbooks you'll ever get will show you a unit circle. That's a one where the radius is 1. And we can look at a general condition where the radius has been rotated here by an amount a. So the radius is length 1. All we have to do is go to the tip of the radius and draw a line parallel to the y-axis until it reaches the x-axis. That means we have a right angle, two right angles here. We've set up a nice little Pythagorean triangle for ourselves. But along with that, what we're going to do now is we're just going to give names to things. That length here, if we measured it, is getting the name of cos A, and this length here will get the name of sine of A. Remember, sine is the opposite over the hypotenuse, and the hypotenuse here is the radius, which is of length 1, so the sine is just the opposite. So opposite A, that length divided by 1 is just that length, so that's why it's sine A. And we know from before which is slope. And the slope we're talking about is the slope of the radius here. What does Pythagoras tell us? Well, he'll tell us that the cos squared length, this bit over here, plus the sine squared length is going to be equal to 1 squared, which is 1. And that's basically the first identity that you're given. Now again, for example, all we need to do is divide across by cos squared. Now, I've just deliberately brought in this second identity because there are 3 other functions that are of lesser importance to cos, sine and tan, and they are sec, cosec and cot, and there is always a little bit of difficulty in the mind of people as to how to remember them, and I'll go through that now in a second. In this case here, what we have is the sec. So how do you remember them? Okay. secret is the third letter. That's an S, so it's related to, it's 1 over the sine. That's a C, so it's the 1 over the cos, and that's a T, so it's 1 over the tan. Okay. Let's look at the relationship of negative angles. Positive rotation, which is a rotation counterclockwise of A, and we look at its counterpart, which is a rotation of the same amount but in the other direction. We're saying plus 1, 1, minus 1. These are taken from the unit circle. So if we're looking at a minus A rotation, and we're saying what's cos of minus A rotation? Well, if we look at it over here, we've drawn our little circle again. Okay. We have put into it the radius going down the way, and we've set up our little Pythagorean triangle. We know that the cos is the horizontal part. So look at it here. That cos is exactly the same as the cos of this angle up here. So cos of minus A is equal to cos of A. However, if we now start to look at the y part for the A angle, the angle up here, the sine is a positive thing. See, it's up here at plus numbers. But in this case, the sine is down here with negative numbers. See, it's below the origin here. So what we can say then is sine of minus A is equal to it is the same magnitude, but it's negative. And tan being sine over cos, and sine being negative, it means that the tan is also negative. So tan of minus A is minus tan of A. Reference angles. If our rotation, our angle, is greater than 90 degrees, for example like that there, we want to try and relate it back to information that we'll know on angles that are less than or just equal to 90 degrees. So there's a hunt to find what the reference is. And for example, one of the examples that we will have obviously is where the angle is this big. And the third one of interest how do we find the reference angle? Well, it's easiest if we get the English instruction of it right, in other words the language instruction of it right. You go to the tip of the radius exactly as we did for the unit circle for defining sine and cos. Okay, we're going to do the same thing. You go to the tip of the radius and parallel to the y-axis you draw a line towards the x-axis. So in other words, we're sending it down there. In this case here, we're going to the tip of the radius and drawing a line parallel to the y-axis towards the x-axis. And in the third case down here, we're going to the tip of the radius, drawing a line parallel to the y-axis towards the x-axis. In all cases, we've now trapped the reference. Okay? Okay. So it immediately tells us something. When our angle A is between 90 and 180, the reference angle is the amount by which it is shy of 180, that it's less than 180. So in this case, we can say R equals 180 minus A. In the middle case here, where we're in the third quadrant, down in this case here, our reference angle is the amount by which A is greater than 180. So here, and when we're in the fourth quadrant, our reference angle is the amount by which A is shy of 360. So we would say what else can we know about these things? Let us deliberately put in our important numbers here. The reference angle is going to be something less than 90. But we need to know if the coses and sines are exactly the same as if the reference angle was over in the first quadrant. This is what we want to refer it to. Okay, we're trying to get each of these three referred across to an angle less than 90 degrees in the first quadrant. This is the first quadrant. Okay, that's the second, third, and we have four quadrants. Well, obviously if you look at the first quadrant, that's in the positive x direction because that's 0. So our cos is a plus. The sine in the first quadrant is off up in that direction, so it's also a plus. Now let's look at the second quadrant, this top drawing over on the right hand side. The sine is plus, definitely. Look at it, it's up here. That is above the y equal to 0 line. So over here sine is plus. However, the cos is negative. Now that means the tan is also negative, because it has to be, because sine divided by cos will be the tan, and the cos is negative, so the tan must be negative. In the third quadrant, well, the sine is down here. That's below the y equal to 0. So we know that the sine is negative. And also, look at over where the cos is. The cos is also negative. So cos negative, sine negative, and therefore the tan, which will be a minus divided by a minus, is a plus. In the fourth quadrant, we can see that the cos is positive. You can see that the sine is below the y equal to 0, so the sine is negative, and so the tan is negative. We can put all that into one little diagram, and we can say the cos, sine, tan, plus, plus, plus. Cos is negative, sine is positive, tan is negative. Down here, cos is negative, sine is negative, so the tan is a plus. Minus divided by minus. And over here, cos, sine, tan, cos is plus, sine is negative, and tan is negative. So we can pick out all of these are plus. The sine is plus over here. The tan is plus down here. And the cos is plus down here. There are various ways of remembering these. The ways I remember them is acts. A, C, T, and S. So then, what we know is that the reference angle is the amount that the main angle is either more or less than 180 or the 360. All the reference angles are between the radius and the x-axis, basically. In the very first example, in the first quadrant, an angle is its own reference angle. It's between the x-axis and the radius. In the second quadrant, the reference angle is between the x-axis and the radius. Similarly in the third one and the fourth one. One last little thing of this kind of general stuff. Here's an angle A. If that, let's say, was a dial on something that looked like a clock, if it was like a hand of a clock, and you walk in and you'd say to yourself, oh well, that's 45 degrees up from the x-axis. You don't know if the person that turned it that far up had actually sent it around several times. And it could be that they sent it around many, many times before it finally finished up where it is. So what we can say is that A is equal to the 45 plus a certain number of full circle rotations. Okay, so then it would be n of these rotations by 360 degrees. Every rotation is 360, so A could be 405 degrees, for example, or much bigger number. Now the quick way of just working these out, if for example we have been asked to work out a question here, cos of 1230 degrees. Well, the easy thing to do is just go 1230 on your calculator and divide it by 360 and you'll get a certain even number. Okay, it'll be 3 point so much, and you don't care about this bit. All that matters to you is that bit, the amount of even number or full numbers of 360. Okay, so what we can now say is that implies the angle is going to be equal to 1230 minus 3 by 360. Okay, and now you have an angle that's less than the 360, so we can play with it. $150 is over here. Let's find the reference angle. Go to the tip of the radius, draw a line parallel to the y-axis towards the x-axis, and this has trapped the reference. So R is a 30 degree. Now we need to know if I find the sine and cos of 30 degrees, is that the same as the sine and cos of 150? Well, over here we know that's negative, the cos is negative. Okay, so cos 150 is equal to minus the cos of 30. And we would also know that the sine is positive, so if we were asked for the sine, you can go sine 150 is the sine of 30. These problems are very straightforward if you take your time over them. If you don't, you're likely to make a mistake. The second, third and fourth quadrant isn't a major issue if you just remember how to trap your reference angle. the sine rule. It's important to remember that there's two ways of writing this, and before we get onto it, if I say to you 7 is equal to 7, that means we can flip them and say 1 over 7 is equal to 1 over 7, and isn't that also true? So we can flip the sine rule. What else do you need when you're dealing with the sine rule, and similarly for the cosine rule, is you need to have a map to know what you're dealing with. The side C is straight across from the angle C, etc. Now, why is it important that we need to consider that there's two ways of writing the sine rule? Well, the top one here is important if we are looking for a length from this triangle over here. If I'm looking for a length of one side, I'll use the sine rule in that shape here, because then all I can do, very simply, I can say A, and to multiply across by sine A, I'll be able to say it's equal to B sine A over sine B. Just one little multiplication will give us an opportunity to work out A. If instead, if I was looking for an angle, we'll just say I was looking for the angle C. We want to have this up on top, so that I can say again, it's one single multiplication across will bring us into the form in each case that we're looking for. The proof of the sine rule is a very easy thing. We can, in our triangle, we can set up a perpendicular. Now obviously there are three separate perpendiculars we are setting up. This is the one that's perpendicular from the side A, and it's a very particular one. It's the one that touches the point of the triangle, the apex of the triangle where the angle A is. What do we know about that? We can call it H for the moment, okay? And the secret in this one is just using the area of the triangle, which is the half base by height. Now, you can work it that way. The easy thing to do here is to talk in terms of, look at sine of B. What is it? Isn't it H over C? Okay. Now if we come across from the right hand side and look at it, the second triangle, we can also say that sine of C is going to be equal to H over B. So we can say and because this is in common, I can equate this directly to that, and I will get and similarly for the A one you can do it. Once you've done this, you've proved your concept. Now the important thing, the really important thing here, is that what we're actually talking about is, when we're looking at the sine rule, is the only way that this can equal that, can equal to that, is if they're equal to a constant. Okay? There's something to watch out for in the sine rule. When we work out an angle using the sine rule, the answer can be ambiguous. In other words, there are two possible angles that you can get. And all of this comes down to the fact that, and I'll draw it in here in the middle, while we have an angle less than 90 like this, we have a positive sign. But if I have an angle over here, that size of an angle, the sign is also positive. So there's two possible angles, and we have to be careful which we're actually dealing with. So the angle can be relating to that nice little one here, or it can be relating to the reference angle over here, so we could have a larger one. Once you recognize that there are two possible angles, okay, a theta and a 180 minus theta, you can address the issue of ambiguity. To prove the cosine rule, we're again just going to be appealing to very basic facts. Now, the secret is one of the sides, in this case it's going to be b, is going to get replaced by two variables. It's interesting that in deriving the cosine equation, we actually bring in two new variables, an x and a y. And the reason why this is interesting is in many of the problems that are associated with this chapter, ones of triangles or even a group of triangles together, to solve many of those problems, the key is to name some side, for argument's sake, as an x. And then we can play and develop up a set of equations, for example, two simultaneous equations, and then solve for x. So even in the proof here for the cosine rule, we're using the exact same trick. What do we know? We know that the cosine of this angle A is x, the adjacent, divided by the hypotenuse, the one that's across from the right angle. Okay? So that implies obviously that x is equal to c cos A. That's the first little thing. This is an easy enough proof, by the way, and it is on the Leaving Cert. You can be examined on this. What do we know for the second bit? And I know what x is. It's this thing. Now, that isn't hard. And we only have two more steps left, which is a nice little thing to know. Pythagoras. What does he tell us? He tells us that c squared is going to be equal to x squared plus h squared. Okay? That's just making use of this here for that guy. And there's only one more step. Second triangle. So you can see the third and the fourth step is basically the same thing here. So now we're able to say, okay, what is h squared? We know that. And we need to find out what y squared is. And we know what y is. So all that's nice and handy, and we have all of the things that we're looking for in here. You'll notice there's A's in here, the C's are in here, we'll have B's in here. So once we multiply that out, it's an easy proof. But it's more important than the proof itself. It's important because one of the things that it shows you right in the step one is if I've got a length like x here with an angle like A, and if I know that the hypotenuse isn't just 1 like it is in the unit circle where the radius is 1, if the hypotenuse in this case is C, it's the exact same as saying I have a radius of C. We know that that length here, the x length, is the radius by the cos of the angle. And by the exact same implication, we can state also that the h would be equal to c sine A. It's just that it's nice and handy, and it's a quick way of working out lengths when you've got triangles where the hypotenuse is not 1. You just, rather than referring all the way back to the definition and the ratios for sine and cos, just remember it straight off. The second reason it's important is the incorporation of those two variables to solve the problem. It would have been very easy to think in terms of, well, I know the sides are A, B's and C's and the angles are A, B's and C's, and try and solve it using that. But just splitting it up makes life easier for us, okay? Just to show this thing about the variable. And this is an example straight from the book, okay, by Rowntree. First off, there are 3 triangles here. Just to make sure you can see this triangle, you can also see that triangle, and there is the main triangle, which I will just draw outside of this big guy. Now, those 3 triangles, to solve these problems, in any one of those 3 triangles you're looking for three pieces of information. One of those pieces of information should be, at least one of them, should have to do with the length of a side. Now, looking at this particular one, definitely I can say right angle here. That means for the big outside triangle I've got 30 degrees on the left corner, I've got the right angle, and I know I'd have for the big outside triangle 60 degrees up top. For the red right angle triangle I can say 90 degrees, 60 degrees, 30 degrees, but unfortunately I don't have any lengths, and I'm looking for h. So what do? This is where you have the exact same process that you had in solving the cosine rule. You give a name to something. Because we have this 100 as the length from here to here, we'll complete that side by calling this x. Okay? And having called it, we can now actually give an expression for it. That's nice and handy. We already know this. Because we know that, we can also now say that I know this full length. It'll be 100 plus that. Now, what we have gotten here are two simultaneous equations. And once we name them, for example 1 and 2, you could name them A and B, I don't mind. You're now in a position to be able to talk to whoever would be examining how you're solving the problem by explaining what you're going to do with those equations in order to solve the situation. So, the nice thing about these two equations is they already have one side equal to each other. So that would imply to us and once you solve it, that's all that's going to come out of it. So it's 50 root 3. It'll be much, well, not much harder. It would have been harder if we hadn't just given the name x here. Most of these simpler type of ones, the ones with two triangles that also form a third triangle, require you to give a name, a variable name to some side. There's a nice little rule of thumb that you need to apply, because in these type of problems you're left with the working out which should I really be applying here. Should it be the sine rule or the cosine rule? And the basic rule, which is again given in Rowentree's book, if you know in the triangle that interests you, if you know a side and the angle across from it, for example, situation like this, where you have an angle and across from it you know its side. If you have that in your triangle, you'll use the sine rule because it's faster. And if you don't have this, use the cosine rule. rather than going through a lot of examples in relation to this, because there's only a small amount that can be learnt by watching somebody else doing them, it's more valuable for you guys to go and do these problems. The issue is recognizing that often the triangle that has the piece of information that's being looked for, that you've been asked to calculate, isn't the triangle that you start with. You'll start with the triangle that has at least 3 pieces of information, at least one of which is a length. And doing that, you will calculate another, let's say, angle or a length of a side that will then populate up information in the next triangle. And you may have to go through more than 2 triangles in order to get to the point that you want. So when you're looking at them, you just plan your campaign. You plan that I need to know a certain length. And then you're saying, if I know that one, it now is useful for another triangle, and that triangle then may get 3 pieces of information, and it means you can proceed. It's a simple enough game. Where these things get complicated is for the 3-dimensional problems. And a standard type of situation is where they'll tell you there is a pole which is perpendicular to horizontal ground. That's just a nice way of telling you horizontal ground means it's flat, like it runs along the x-axis basically, and the pole is perpendicular to it. So the trouble is, it's very hard to draw these things in a 2-dimensional sense, okay? Because if we look at that now and we're saying, yes, this is the pole, clearly it's at right angles here to that direction, but it's also right angles here, and it's also right angles here. So visually looking at it, you may not necessarily be able to see the right angles, but you draw it as well as you can. Now, the type of situation that you will have is where you will know some other lengths. The important thing here in a situation like this is there are 4 triangles. You've clearly got this one in the background here between the pole, this horizontal line, and running off up along here. You've also got another one between the pole, that horizontal line, and running down along here. Then you've got the flat one, the one on the ground, which I'll show with a different colour. And the third one then is this blue one that's facing us. That's the nearest one. One of the most important things when you're solving these problems is, just because it's one problem with one diagram on it doesn't mean you're limited to one drawing. Draw a lot of drawings, and for example, if I wanted to deal with the one in the background here, sorry, I'll use this one in the background here. If I want to deal with that one, what I would say to you is, it's always useful to put a little dot in it and draw a line down, and then redraw. And name the bits that you know. This is obviously the pole. Now you can see your right angle nice and clean. The same way, this base one down here, you can draw that one any way you like. And we know that the pole is sitting here vertically up from the screen, so you don't get to see it. Now you can populate in the information that you need for it, okay? And similarly for any of these particular ones. Now, because there are 4 triangles here, you may have to transport information from one through a calculation of a side or an angle into another one, and then from there across into another one. That's why these little extra drawings are very useful. These ones with a pole are not the most complicated ones you can get. For example, you can be given a pyramid. that type of thing. Now, in this pyramid, you can be told that the top of the pyramid has a pole going up to it from the center of the base. If they tell you the center of the base, and for argument's sake, if we knew that it's a square base and that this is 6 in length, and now it doesn't have to be 6, 6, we'll just, even for the moment, even call it 8, 6. Okay, we'll put this one as 8. If that's coming down, the pole coming down to the middle, what you can do is you can always draw additional lines, and the secret to solving these is to draw a lot of additional lines, once to make life easy for yourself. Okay, when we've drawn this cross in the base and we've divided it into 4 quadrants, we know that that length now is 4, that's 4, and we know that the lengths this way are 3 and 3. What does that allow us to do? It allows us get closer to the kind of question that they may ask us. They may be saying to us, if we pick one of these sides, like this front side that we have here, and they may say, that sloped side, find its angle, find the slope of it. Really what they're asking us is, what's that angle? We've got a triangular wall that is sloping, that touches the pole, and they want to know that sloped line, what angle is it making with the horizontal ground? While we just look at the walls of the pyramid, it actually is quite difficult to work it out. The ways I always look on these things is I imagine that other walls get built. Okay, for example, we would like if there was a wall down through the middle of this here, a one that goes in as far as the pole and all the way up to the top. So we've this little triangular wall here. Having got the triangular wall, we know, having it drawn, we know that our angle is simply something, it's constructed along that particular triangular wall. We, for argument's sake, can get problems such as, if we look at a rectangle now, the kind of really difficult problems with these ones is where they say to you something like, from the bottom corner at the back, what's the length all the way up to the top front corner? You will notice that that line doesn't, you couldn't paint it on any of the 6 sides of this rectangular shape. It's a line that's drawn in space. Okay, if we go back to that concept of build additional walls, a painter can't build or can't paint on a wall unless there's a wall there. So what we would say, what wall would we need to build before we can actually paint this line? And that's an easy problem to solve. And the problem is solved by saying, I'd need a wall where the foundations of it goes from the back left corner to the front right corner, and where the top of it goes from the top left back ceiling part up to the front. Now we're saying, if I build that wall, this wall here, now a painter can come along and paint that line. Why, that's of use for you is we can't get information on that line unless we get information on other things. And one of the things that we may be asked for would be, or we might need to find out, is that type of an angle, or this length of the wall here. Because if we find that length, we will now also have the height from the base up to the top, and we've found ourselves a triangle that will allow us solve what we were originally asked, which is that length. So the trick is, as far as I see, is any time you're asked to calculate something, if it's possible to imagine that there's an additional wall there, a one where it's easy to get information on something to do with the wall. For example, that base length of the wall here. Well, if once I know the depth of this box, and I know the width of this box, and I know my angles are 90 degrees, I can easily work out that length. And having worked out that length, I know the height of the box, so therefore I can work out the diagonal length I was looking for. Again, down here on the one with the pyramid, we're saying, having constructed this triangular wall, the angle we're looking for could now be painted down along that diagonal wall. So we know the length here is now 3. We will have worked out the height of the pole, or it may have been given to us, and therefore we're in a position to very quickly work out things such as an angle, and we can also get this length all the way down along here. That one would easily come out from Pythagoras once we know the other two. So fundamentally, these kind of three-dimensional problems are really solved by imagining extra for walls, for example. And what you got to do with them is, especially when you have a drawing where you have a projection which doesn't show 90 degrees as 90 degrees in many cases. For example, down here, that's a 90, but it doesn't look like it. You go, and if you want to see that wall, you draw a new drawing. And that new drawing will give you your right angle. You will know this is the height of the pole again, this being the pole. And we'll say, I know the base length is 3, that's that length here. So we can now see how it's much easier to look at it by imagining this extra dimension that we looked for out in a single two-dimensional drawing out here. Anything you require, try and pull it out in the second drawing. I would hope to think that the concept that has always worked for me on these, particularly for problems like this box problem over here, where you're going from one corner diagonally through the free space inside, contained inside, to the furthest corner from it, those kind of problems. The building that extra wall, and then knowing that you can populate information on the wall, such as its diagonal foundation length here, that when you get the information on that wall, then all you're now looking at is a simple diagonal of that wall. Those kind of problems, if they are solved, or if they become easier for you using this, I'd be very happy with that, because I know that they are a source of a lot of concern for people. I generally find that I turn the three-dimensional problems into two-dimensional problems. Again, going back to the box, having built that new wall, I'm now looking at this triangle which is down lying flat on the ground, a two-dimensional problem which I can draw, and I'm looking at a triangle which is half of the wall, for example, which I can also draw. So change three-dimensional problems into two-dimensional problems. Other than that, the only help I can be to you on this is later on, once we've covered the chapters as we're going through them now, we'll be covering all of the past questions from the Leaving Cert for maybe a 10-year period, perhaps 15 years. If I find a one that was difficult back, let's say in 97 or something, I'll show it to you. Okay, I'll leave it at that, and I wish you well on this stuff. Bye now.